Okay, so our next speaker, Chayne Planiden, and he will talk about new gradient and Hessian approximation methods, also for derivative-free approximation optimizations. So please.
Thank you very much. Hello, everybody. Yes, I'm quite happy to be in this section because I will also be speaking about the same sort of subject, the VOO algorithm in specific. And some of you here have already seen this talk because I gave it at the MoCal seminar series a few weeks ago. So I will not be offended if you go for your coffee now. That's just fine. So new gradient and Hessian approximation methods for DFO. So let's talk about the VOO algorithm and how it's composed first of all. So we use the Morrow envelope and the proximal mapping of a proper LSC function. The objective function is proper and LSC. So here's the definition of Morrow envelope. It is the infimum of the function plus this quadratic penalty function. And then the proximal mapping, which in the convex setting is just a proximal point, it's a unique point, is the set of minimizers. So we find these elements quite useful for many reasons. The Morrow envelope is a smoothing function. First of all, it will smooth out all the non-smooth kinks. Well, not all, but the sort of exterior facing kinks in your non-smooth function. But it keeps the same minimum value and the same minimizers. So it's a method of smoothing out a non-smooth function, and then once you do that, you can use smooth techniques to minimize your function instead of having to deal with non-smooth. The gradient has a very nice closed form. It's on the next page, I think, or next couple pages, for in the case of convex functions. There's a parameter r that you can play with here. This non-negative parameter here, you can choose. And as you change it, as you increase it, you get a closer and closer approximation to your original function. So it's also an approximating function. And you find the proximal mapping all over the place in many different types of optimization algorithms. We've seen today, in particular, proximal point algorithm and its variants. So here's a very simple non-smooth function. It's the absolute value function in one dimension. And for a function like that, you can quickly work out the Morrow envelope. It's not too difficult. And you can see that it's linear for a while, and then it becomes quadratic in the middle, and then linear again. So you get this envelope effect, and that's why it's called an envelope. It has the objective function sitting inside it, like a letter in an envelope. And so it's nice and smooth, but you can see that the minimizer is in the same place. So this red curve is for parameter r equals 1. That's called the prox parameter. If you increase the parameter to 2, you get the blue curve. And if you go to 5, you get the pink curve, and so on. So you get this effect of more and more closely approximating your function with a smooth function, as closely as you care to do so. So if your function is convex, this is the formula for the gradient of the Morrow envelope. And P is just a proximal point. So the proximal mapping is just a single point if your function is convex. So nice and simple. And then you have converted your non-smooth problem into a smooth problem. So some of the things you can do with this. This is one of the projects that we did last year, converting norm functions into smooth functions, or mostly smooth except for in one point. So if you take a norm function, any norm function at all in Rn, and you square it, and then take the envelope, the Morrow envelope, and then square root, what you come up with is again a norm function. It's a new norm function, but the difference is it is smooth, differentiable almost everywhere except for the origin. There's no hope for the origin itself, unfortunately, but every other point becomes smooth. So here are a couple of typical non-smooth norm functions, the infinity norm and the one norm. They have these non-smooth ridges, in every direction. And if you apply this envelope method, what you get are functions like this. So the dark blue is r equals 1 parameter, and it's smooth everywhere except for at one point. And then the sort of less blue and more gray ones are just the same envelope function, but with different parameter, r equals 2, r equals 5, and so on. Okay, so minimization algorithms. One of them is the proximal point algorithm, which I'm sure most of us are familiar with. And it's beautiful in its simplicity. It is this one line basically. The next iteration becomes the proximal point of the current iteration. That's all you have to do. Find the proximal point of f at the current point. That becomes your new point. So the idea is here's a non-smooth function. It's convex but non-smooth, and here's a starting point here. So you find the proximal point. So you add your quadratic penalty term to the function, and then minimize that. Find the infimum of that function. And so here's the proximal point. So that gives you a second point in your sequence, and now you repeat. So now at this new point, you add in your quadratic penalty, minimize that new function, and you get a third point. So you get this sequence of points that marches along towards the minimizer. That is basically the proximal point algorithm. So it can be difficult to find proximal points. It's not, I don't want to give you the impression that it's very easy to do. Depends on the nature of your function. So if it is too difficult, what we typically do, as Claudia will happily tell you, is use a bundle method. So proximal bundle method, what happens there is you approximate your function with some model function, usually a linear, like a piecewise linear function. And instead of finding the prox point of f, you find the prox point of your model. So that's called the proximal bundle method, and the bundle is the collection of information that you collect along the way. So at each point, you're grabbing like a subgradient and putting in another linear piece, and so you increase your bundle at every iteration. So here's a graphical representation of that. This is just moving to finding one proximal point. So here's your starting point, and let's say that this over here is your proximal point. But you can't find the proximal point directly for some reason. It's too complicated, it's too costly, whatever. So what you do is use the bundle method instead. So instead of using the black curve, you approximate it with a model function. So at first it's just a linear function. The first iteration is just a straight line function. And then you find the prox point of that. That's very simple to do, finding the proximal point of a linear function. So there it is, and there's your march towards the actual true proximal point. So now that you have a new point, you add another piece into your bundle, and now you have a two-piece linear, piecewise linear function that is your model. And it's a little bit better model than before. So now we find the prox point of this model function, and we get a third point. And we use that to improve our model again. So now we have 3 different linear pieces, and so on. So this is the bundle method that builds an ever better approximation of f and finds the proximal point of f at this original point by iteratively finding proximal points of the model along the way. That's proximal bundle method for finding prox points. So proximal bundle methods are very common for subroutines in many optimization algorithms. And so what we work on, I and my co-authors, Warren Hare and Gabriel Jarry-Bolduc, we work on derivative-free methods, conversions of methods like this to methods that do not use derivatives, don't use first-order information, and instead we use approximations to derivatives or subgradients. And in particular, we are interested in the derivative-free VOO algorithm. So this was mentioned already by Claudia, who is one of the creators of the method. It's the way of taking advantage of the structure behind the function to speed up this minimization process. So what we wanted to do last year was to make it derivative free. We have accomplished that now, and I won't spend too much time on that because that's last year's news. So we succeeded in instead of using like this exact gradients to build a model, which gives a nice minorizing function, we use approximations to gradients to build our model function. And so one of the pitfalls you get is you no longer have a minorizing model function. You get this kind of situation where the model might be up into the epigraph of the function. And that's usually a problem. So you have to deal with that. I'm not going to speak on that anymore because that's, as I say, that's last year's news. You can look that up if you want. But it's just one of the things that you have to watch out for. Okay, so the purpose of building the DFO proximal bundle algorithm, which we did, is to develop the DFO VOO algorithm. So as we saw first thing this morning from Claudia, prox point algorithms are slow. We're stuck with possibly superlinear in case of the nice VOO algorithm for convex functions, but usually linear or even sublinear convergence speeds. So what VOO attempts to do is to speed up the convergence by splitting the space apart, what we call VOO decomposition. So we identify the non-smooth behavior of the function. We localize that to just a subspace of Rn, which we call the V space. And then we deal with that separately from the U space, the smooth portion of the function, in which we can do a fast step, like a quasi-Newton step. So we get some speed in doing that. Okay, so we're taking advantage of the structure of the function, because usually the non-smoothness of the function is due to a subspace only. So here's a little graphic in 2 dimensions. Here's a function that is smooth in the x direction, but it is non-smooth in the y direction. So depending on your point of view, if you look at it from the point of view of x or of y, you get either the V shape or the U shape, which is where the VU algorithm gets its name. And we can take advantage of this. So the original VU algorithm is this. You do some initialization, starting point and whatnot. You find the decomposition, the VU decomposition of the space at the current iteration point. So this decomposition will be different for every single iteration point. So you have to recalculate this every time. And then you run what we call the V step. So in parallel to the V space, the problem direction, the non-smooth direction, you do a proximal pointing method, a proximal bundle, whatever you are going to use to deal with the non-smoothness. You do a stop check. If you're close enough, if your subgradient norm is close enough to 0, then you stop. And if not, then you do a U step. You go to the the perpendicular, the orthogonal U space where the function behaves smoothly, and you do a fast step, like a Newton step. So you solve this typical Newton equation for delta U, and you take a step in that direction. And then you repeat. So you do a V step and a U step and a V step and a U step and a V step and a U step in this sort of zigzag fashion, and you get convergence to the minimizer faster, superlinearly. So this algorithm was proved by Claudia to have superlinear convergence speed for convex functions. So here's a non-smooth function that has sort of a flat section here, parabolic flat section, and the minimum is down here. So if I turn this to bird's eye view and you look down from the top, the minimum is here at the vertex. And what the VU algorithm does is, given whatever starting point, you take a step in the direction of the smooth manifold. This black curve is the manifold here. So you take a step directly down to the manifold, and then an orthogonal step towards the minimizer. And that involves decomposing the space into the V space, U space, so that you find this direction, the V direction, towards the non-smooth bit, and then the orthogonal U direction. And then once you're here, you do that again. So you drop down to the manifold, and then you go towards the minimizer, and then drop down towards the manifold, and then go to the minimizer, and so on. So in this sort of zigzag fashion, you get convergence, superlinear convergence down to the minimum. Okay, so 2 points. The V step requires a proximal point, which involves first order information, subgradient. But that can now be approximated by our proximal bundle method. That's the last year's news. The U step also requires first and second order information. So we use a gradient and the Hessian just in the U space, in the smaller, the reduced space, to do this Newton step. And so in the DFO version that we built, we also approximate both of those. We use now an approximate gradient using the simplex gradient, and an approximate Hessian using the minimum Forbinius norm problem. So here are some details on that. For those of you who don't know or just need a refresher, simplex gradient, the idea behind simplex gradient is to linearize your function. You build a linear interpolation function close by the point of interest. So you need n+1 points in Rn to do that. And then you take the derivative, or find the gradient of the linear function, the affine function. So if this is your function and your point of interest, you take 2 more points. This is 2-dimensional, so you need 3 points to build a linear interpolation function. So there's the affine function, and then you just find the gradient of that. And that is your approximate gradient of this original function at the blue point. That is the simplex gradient method. Okay. So here are the algebraic details. You build, so this nabla S is what we're calling the simplex gradient of the function f over the set x. X is your set of n+1 points. And so you build this n by n matrix S, which has to be invertible, and you take S inverse times this delta function. Delta is the vector of the difference of function values, the respective function values that correspond to these points. So that is the simplex gradient, the product of S inverse times delta. So typically you can take, for example, coordinate directions, a certain step size in each coordinate direction. That gives you a nice linearly independent set here. And that will form a simplex that will allow you to calculate simplex gradients. And the condition number is the norm of this S inverse matrix. S hat is just S divided by delta. Delta is the radius of the simplex, the maximum distance between 2 points in the simplex. And the condition number is what keeps this method from degrading as you're approaching 0. You can make delta arbitrarily close to 0 and your method will still function. So there is an error bound between the simplex gradient and the true gradient of the function. It's nice and simple. So you take the norm of the difference of the two gradient methods, and you get a constant times this condition number and times delta, the radius of your simplex. So you can control delta and thus control the approximation of your gradient. And then for the Hessian, we do something similar, but it's second order. So we solve what's called the minimum Frobenius norm problem in that case. So here's the definition of the Frobenius norm of a matrix. And we did this work for finite max convex functions only, so to make the calculation of the V space a little bit simpler, more accessible. So finite max function, that just means you take a bunch of convex functions and you take the maximum of all of them. So you end up with something that looks like this. It's convex again, but it's obviously non-smooth. So this is typical structure of a finite max function, and the subdifferentials are rather easy to calculate for finite max functions. That's why we use them. So the minimum Frobenius norm problem is this. You need 2 n+1 points instead of just n+1 points. So typically you take coordinate directions plus and minus by some step size, the radius of your simplex. And then for each active function, for each of these active components here, you solve the minimum Frobenius norm problem. So H, B, and C are the variables. Z is known. Z is a column. Zj is column J of this Z matrix. And you find the argmin of the norm of H matrix here. And that is the Frobenius norm Hessian for one active function. And so you do that for all of the active functions at the point. You take the average of those. That's what's happening here. And that is your H, which is the approximation to the Hessian of the function. And so we call that U Hessian because we are concerned with the U space only where the function is smooth. So Hessian exists. And so H is our approximation to the U Hessian. And then you do this conversion into the U space to get it to be U dimensional instead of N dimensional. So you can also prove, just in the case of the simplex gradient, you can also prove that the Frobenius norm has a nice bound. It's more complicated looking, but really everything in here is constant. And so it's really just dependent on the radius of the simplex. So once again, you can control delta and get a nice approximation to the U Hessian as closely as you want to. So the derivative-free VOO algorithm is much the same as the derivative-based one. Just the differences are in red. So you have the radius of the simplex as a factor in your stop check. And instead of using the actual gradient, you use the simplex gradient. And instead of using the Hessian, the U Hessian, you use the approximation, the Frobenius norm approximation. Everything else runs the same. And you can prove, which we did, that this also converges just as the VU algorithm does. We don't claim superlinear convergence, of course. So I can't imagine that will be true. We haven't gone that far yet, but we hope for linear convergence. We don't know that yet. So the new information that we've done this year now is how to get new approximations, how to better these gradient and Hessian approximations. How can we do that more efficiently? How can we get better accuracy? So what we did was generalize. So we start with the first order information, the simplex gradient, that we base our VOO approximation of the U gradient on. So you can use the generalized simplex gradient instead. And the generalization is you don't need to use n+1 points in Rn. For the simplex gradient, you need exactly n+1 points, and they have to have some nice certain structure, be properly spaced out. But you can generalize that to use either more or fewer than n+1. And you still get a nice approximation to your gradient. So using k points, k could be either more or less than n+1. You define the generalized simplex gradient like this. So instead of using the matrix S, we can't anymore because it's not square, because k is different from n. So we have to now use the Moore-Penrose pseudo-inverse of S instead of the actual inverse, because there is no inverse probably to a non-square matrix. Well, certainly. So everything else is defined the same, except that we're now using pseudo-inverse instead of inverse. And we proved this theorem that the bound is very similar to the case of the regular simplex gradient. It's just that, of course, it depends on the number of points that you use in your simplex. And again, it's a function of delta, the radius of the simplex. And in here now you have the Moore-Penrose pseudo-inverse, the norm of that, and L is the Lipschitz constant of Nablayev. So we require C1 plus functions. So we have to have a continuously differentiable function so that the Lipschitz constant exists. And then the second method that we considered is called the centered simplex gradient, which is a simplex technique also, but it greatly increases the accuracy. So what you do is you are required to use more points than n+1. That's the drawback, if there is any drawback. But I think it's well worth the penalty. You need 2 n+1 points instead of n+1. But the error bound is a function of delta squared instead of delta itself. So that's huge in my opinion. That's a very big gain, and it's well worth requiring another n points. So you use the simplex as before. The same simplex as before. You can rewrite it in this manner using x0 as your point of interest, so x0 plus a little piece. And then you take what's called the reflected simplex. You subtract all of these same numbers, these d vectors, and you obtain another simplex. And then you create the centered simplex. So you take the difference of both function values as before, and you define the centered simplex gradient as the inverse of this matrix S times delta C, same as before, same general pattern as before. And what you can prove is that the centered simplex gradient is in fact the average of 2 regular simplex gradients. So you're taking one simplex gradient, the one that you took before, you're taking the reflected one nearby, and you're averaging the 2 out. That is the centered simplex gradient. And further to that, you can generalize this process as well to using any finite number k of points instead of n+1 points, or in this case 2 n+1 points. You can use more, you can use fewer, and you can still prove using now the pseudo-inverse instead of a square matrix. You can still prove a nice error bound. So here's the visual of the centered simplex. This is the same as before. Here's the linearization that we saw before. And then you take the reflection of these 2 red points about the blue point. You take the reflection and there are the other 2 points there. So you define the other linear function as well. And you find those 2 gradients and take the average. So your accuracy is improved by an order of magnitude on delta. So we proved that in both the overdetermined case, which is k bigger than n, and in the underdetermined case, which is k smaller than n, that you can obtain these bounds, these error bounds, for the centered the generalized centered simplex gradient. So once again, it's a function of k, the number of points you use, and delta squared, and then your norm of your Moore-Penrose inverse, and your L, which is your Lipschitz constant of the gradient. So that is a pretty good improvement. This is the reason that you get the order delta squared, because in your Taylor expansion of these two things, when you do the centered method, you get cancellation because you're moving in the two directions. The first term, the first order term of Taylor expansion cancels out. So you're left with just the second order term. Okay, we also created, 4 minutes left. Okay, let's speed up. So we created some calculus rules. So you can calculate generalized centered simplex gradients for product of functions and get similar error bounds. And also for quotient of functions, there's a quotient rule, and we have a composition rule. And all of them give the order of delta squared. So your simplex radius squared it's what's determining the accuracy of the error. Okay. And then finally, the very new thing is that we did the same thing for the Hessian. So we want to improve the Hessian calculation. We created what is called the nested set Hessian, which is a similar process. You just need two sets of directions instead of one set. And you can generalize both of them to any finite number of points, the same as the simplex gradient. So we call them S and T. And then you take all of these kinds of points, they all have to be in the domain of F, and you form a similar structure. You have the delta function, the difference of function values. You have the you find the simplex gradient, and then you find the gradient of that again, the simplex gradient of that again, basically. And then you calculate an error bound. You can make some careful choices of your two sets and get the number of function evaluations down to this minimum number. And then we find an error bound that is on the order of delta. We don't get delta squared this time because it's second order information. So, but we get an order delta approximation of the Hessian, of the true Hessian. Again, it's dependent on the number of points that you use. And the Hessian, now we need the Lipschitz constant of the Hessian. And again, we did calculus rules for the product, for the quotient, and for the composition of functions. So in summary, you can generalize these simplex methods and the centered simplex methods to improve your order of accuracy by an order of magnitude. And you can do the same thing for the Hessian. It doesn't get you the quadratic order, but it gives you a more general way of finding Hessians. And it's not so restrictive as the Forbinius norm, because Forbinius norm works very nicely for finite max functions, but I don't know about other classes of functions. And this nested set Hessian will work for, as far as I know, not any restricted class of functions. So we haven't done numerics yet. That's forthcoming. And in fact, for that, I need a PhD student to help me. So if there are any students out there that are interested, please give me a shout, and we can work on convergence speed of this work that we've just done. So thank you very much, and I'm happy to take any questions.
Okay, thank you very much, Chayne. So any questions? So we have time for 1 or 2 questions.
I have a question.
Go ahead, please. I have trouble hearing you, but go ahead.
Yeah, that's a nice result. I wonder how would you exploit it algorithmically, how to decide how many points you would use along with
Yes.
which criterion. Because your K is a number of points that you are using, is that?
Yes, that's right. Yeah.
So, it seems that the more that you use, the larger is the bound.
That's true, and actually, that speaks to current work that we're doing. It looks like this error bound will go to infinity as K goes to infinity, right? So that's a problem. That's a problem. But we are working on that, and we have, in fact, 2 papers in the works about how to get around that. So I'll have to say to be continued on that point, I guess.
In the next one.
Yeah. But the point of K in the VU case is we want this process, we want to use this process for the U space, right? So K will be the dimension of U. It will be reduced, it will be smaller than N because we only have to work in the U space. So that's sort of the VU point of view of K. You don't have to use N plus 1, you could use U plus 1 points, for example, to work in the U space.
That's good. Thank you.
Thank you.
Okay, so more questions?
Sorry, maybe I have a short question, Chayne.
Hello, Regina.
Thank you for your nice talk.
You're welcome. You've seen it twice now.
Sorry?
You have seen the talk twice now.
Ah, okay. Well, maybe I finally understood some things. Look, I have maybe, forgive me if my question is inaccurate. When you construct a simplex gradient,
Yes.
can it be that I know that you are working with functions which are differentiable, but can it be that the simplest gradient at your reference point is the epsilon subgradient of the original function at some other point?
That would be possible. I don't, as far as I know, I can't make that happen, but yes, it possibly could be.
For a given epsilon and a given point, because you are doing some kind of translation, and maybe you could use the formula for epsilon subdifferentials. The transportation formula.
Using this as your epsilon. Yes, that's an intriguing thought.
It might help because that will give you a value of the epsilon and you might have some control on that value.
Yes, very good. I'll make a note of that. Thank you.
You're welcome.
Not inaccurate at all.
Thank you. Thank you.
Okay, so I guess we don't have much time left, but Slack is available. So thank you very much, Chayne, and we are waiting for the results of your numerical experiments.
Yes, thank you very much. I'll maybe by next year's conference, certainly by next year's, or maybe sometime